So I was going to create a poll here, but my Zoom wasn't cooperating. So just a quick question. There's 20 of us here or so. If you could just in the chat window indicate, if you're using Rspec today, if you could type yes in your chat window, that will give me an idea as to what the background of the attendees are. It'll stream past. There's a couple of yeses. Jim, there's Barbara, Serge, Paul. Great. Thank you. Appreciate it. Not yet from Tulio. Patrick. Hi, Patrick. Nice to see you. Great. Hi, James. Okay, so we have somewhat of an even mix. And it's a bimodal group. Hi, Jay. It's bimodal, and it's a little bit challenging to speak to a group like this. What I'm going to do is go through Rspec and show just a simple image capture and spectrum processing, show what it does. Hopefully, those of you who are familiar with the program will learn a little bit. There's plenty to be learned for all of us. So, you know, having just seen David's presentation and Catherine's earlier today, I don't literally feel chastised, but I you know, I always wonder how you know, energetic should I be? That's my natural mode. But these gentle chats that we had this morning are really, really nice. And this, I was anticipating this being more of a fireside chat session. So I'll do that. I don't know if Olivier's here. We'll play it by ear. I'll try and keep my chat window open. Feel free to ask me questions. Let's see. In fact, why don't you put them in the Q&A window? That'll be easier for me to see. And I'll try and respond as we go. I was hoping this would have a bidirectional audio so we could do that, but in webinars and Zoom, we don't have that. By the way, I'm going to institute something like this for Rspec on a regular basis, where people can get together and share their spectra and ask questions, or, you know, just be a fly on the wall and watch what people discuss. It's a way to build community, and I think given the social distancing we're doing today, these days, it will be especially welcome, and I think it'll be enjoyable. So watch our forum for that announcement. So let me share my screen here. And you can see I have Rspec running. Great. So, and I've got some notes here to go through this. You know, the one thing I wanted to point out, one of the things that isn't all that necessary to have this webinar today because of, what a sentence, is the video library. So this is opened all the way up. There are a lot of videos here. And you can, as many of you know, you can play these on your computer. If they're not there, you can download them from the screen. It will give you that option, but they're also available on the site. And just to give you a little bit of background, these videos, it always astonishes me how long it takes to make them. I've been making them for about 20 years in other jobs and careers that I had in programming. And they've, as you know, always been enormously successful. Not that you would know before Rspec, but they're really effective training tools. What surprises me is how much time it takes to make a good video. It takes, and this is pretty much the industry standard, to make a tutorial video takes, for each minute of video, it takes about 2 hours of time. And, you know, there's, you know, a video like this might be 5 minutes long. It's going to take me, you know, more than a day to make that video. Because these days I am writing a script. In the past, I would just ad lib, but I find the scripts a little bit easier. It's maybe not any faster. And record it and get the data right, and then I have to go back and I redo the audio over the screen recording, and that gives it the punch that it has. Some people may not like that punch, but they are time consuming, and the call outs, all of that takes time. I'm not going to be able to do better than the videos here, but hopefully I'll do a sort of an assemblage of things that are in the videos that will help you. So the other thing to take a look at if you're not familiar with is the user manual, which is really a very short PDF that I wrote to answer all the questions I've been getting over the years. And by the way, thank you all for coming today. I appreciate it. I'm keeping my eye on that Q&A window. And I'll also, if I can, open the chat window. Actually, the chat window is not available right now, so that's fine. Let's see. Yeah, that's okay. So the options in Rspec are to either use a static image file, which could be a FITS file or a Jpeg or RAW file, or to use video. I'm going to do mostly an image file today. Notice that you can change the width of the screen here, something which some people aren't aware of. Once you're done with this area, there's no reason to have it take as much of the screen as it is. The first image I'm going to open would be a typical image you might capture. Now, this I don't document very well anywhere. I've been thinking of making a video on this, and hopefully this will be the start of that. Notice that when you capture an image, not only do you have the star, but you have spectra on both sides, and that's the way diffraction gratings work. This is called the zero order, and these are called, both of these are called the first order. And these gratings, the star analyzer gratings, are what's called blazed. Now, I want to emphasize that Rspec can be used and is used by many people with higher resolution slit spectrometers. And I'll show you some examples of that later if we've got time. We're going to focus on the star analyzer, which is often the entry point for people. So the blazing, that's a technical term you'll never need to use, but or here again, the blazing directs more of the light to one of those first orders than the other. And so clearly this is the one we'd want to use. It makes it more efficient. Now, in terms of this being an angle, again, a grating is going to project light in two directions, but which of those directions it is depends on how you've threaded the grating onto your camera. And the grating has this little mark there, you can see it, which is a guide. It's not a critical guide, but what you do is when you thread your grating onto your camera, as a first approximation, just thread it so that that mark is horizontal with the width of your camera and pointing, as you're pointing to the south towards the horizon to the west. And you know, it might end up being not at this steep an angle. It's not likely to be perfectly horizontal the first time you go out. You don't need to fix that on your camera for now. You can use the rotate command in the software, and that's this button here. By the way, I don't know if this is helpful, that little focusing thing. It's a little distracting. I made my mouse bigger, and I looked into software that would put a spotlight on my mouse, neither of which really seem to help. But when I click on this rotate button here, I can rotate the spectrum around, and by convention, you want to have the spectrum on the right, the brighter spectrum that you're going to use. In fact, you can even just put the star over to the left so these aren't even visible. Notice that there's a second order spectrum here too, which is also typical of gratings, and we'll be ignoring that. Okay, so now we've rotated into place. I'll close the rotate window for now. And the next step, let's just look at my notes here. Oh, again, a hardware detail if you're using a grating. Once you've spent some time trial and error, not necessarily on the first night, and gotten the grating rotated so that you don't need to apply rotate in the software, then you can secure it, and Robin Ledbeater, the designer of the star analyzer, suggests either some Teflon tape that's used in plumbing or the silicon putty, just a daub or hot glue even on the threads, just a tiny daub, not enough to seal it up for good, to hold it in place. It's a good idea at some point to get your grating horizontal so that you don't need to use rotation for a couple of reasons. First of all, it's much easier to point your telescope if you're aiming and using a control of any sort, whether it's a handheld controller or the manual controls on your telescope, physical controls. It's really confusing if you have rotating in place and you try and change your field of view on your telescope. So it's a good idea to get this horizontal. The second reason is because rotation can introduce a very small amount of periodic noise. It would look something like this, but probably not that large of deviation. And it would be continuous through the whole spectrum. It's very evident when you have it. And that's just an unavoidable outcome of the geometry involved in rotation. So once you have your spectrum, and again, I apologize for referring to my notes here. The next thing you can do, the imaging is, for spectra, is really very similar to the imaging that you've done in the past, if you've done any. There's really not a lot of complications or differences. It all comes down to exposure levels and focus. Now, the good news is, for a long time, you won't need to be dealing with all the things that David was talking about in his previous talk, and that many of you probably do if you're doing advanced photometry, and that is darks and other kinds of post-processing of your image, flat fields. Those aren't necessary. In more advanced work, we can do that. But as you've heard, my emphasis really is on, let's see. Anonymous attendee says he'd be afraid of putting any substance on the threads for fear of outgassing and other things getting onto the naked element of the camera. Teflon tape. Good point. Teflon tape will work fine. I guess you could seal it and let it sit for a day, and hopefully most of the outgassing would have been gone. Let's see, and it took me a minute to see that. So again, it looks like the Q&A screen will work. So in terms of imaging, I don't want to spend that much time on the imaging issues, but it turns out the imaging issues are actually more time-consuming than the actual looking at the spectrum, as we'll see in the next 30 minutes or so. So the first thing I'd like to look at is exposure levels, and you can see clearly that the exposure levels are different on these two, and we expected that, as I described earlier. One thing is, you would continue, if you're a static fits imager or you're using a DSLR, continue to use the camera control software that you've always used. If you're using a DSLR, there's Backyard Nikon, and Backyard is a Canon. About a $40 program, if you're not familiar with it, is a little better than the software that comes with those cameras from the vendors. There are other imaging programs, of course, especially for standard fits cameras. But continue to use that software. I never really wanted to, definitely didn't want to reinvent the wheel with this program. There's people who've spent thousands and thousands of hours making those programs good. So, but what you can do, and I think I mentioned this yesterday, is use your standard, for example, fits imaging software, whatever software you're using. But you can configure the software with this checkbox to automatically open any file that appears in a folder that you choose. And you can see on the little floating help below my mouse there that right now it's configured by default to a capture folder. But you can change that on the options screen here. And Backyard EOS, that's the name, thank you. And Patrick's asking, isn't it better to be slightly 1 degrees west or east so the Rspec will only have to correct one or, yes, yeah. Definitely correct it as closely as you can, Patrick. Thanks for the question. The question is not being possible to get the angle perfectly horizontal. Isn't it better to be slightly 1 degrees west than east, you're saying, so that Rspec would only need to correct 1 or 2 degrees rather than 180 or 190? That's really just a matter of whether you drag this down to here or to here. It's no more expensive computationally for the software to rotate a long distance or not. Thanks for the question, Patrick. I'm glad I read it out yard. There we go. So where were we? Oh, we're talking about exposure levels. So and the fact that you can configure photos to automatically open here. It's really nice, especially early on, to get immediate feedback for your focusing, because focusing is a little different with spectra. So let's look at exposure levels here. And the software has built-in, let's move that out of the way. In fact, I can get rid of that for now. Has a built-in histogram intensity tool. This is a pretty unexciting one. Let's bracket in the region that we want to study, which I sometimes take for granted because it's done so often. But you can see I can grab the lines, either move them together or move one at a time by clicking above and below. And those functions are described under that button there. So snug them up fairly close. Don't really crowd them in, but snug them up fairly close. Is that scientific? No. Again, what you're going to be doing here, the purpose of this workshop is to talk about getting started and how to do spectral. When you finally get into doing the kinds of science, if you choose to go that direction with a slit spectrometer, there's a whole data reduction and capturing process that's much more scientific and more repeatable. But the pleasure that you'll have here is seeing just how forgiving things are. For example, we just bracketed this in. Let's just look at that for a second. We actually can see some absorption features there. They're not pretty, but we can see them. And by the way, so this data is that, of course, and the star is that peak. And this peak here is that second order, as is that. So, but the data certainly isn't very interesting here. You know, the dips aren't very deep. And again, dips, of course, I mean the absorption features. That's probably an artifact from the color Bayer matrix. Color cameras will often have, almost always have, this deep dip here that we just ignore from the optics of the Bayer filter itself. We do encourage you to use mono if you have mono available. The wavelength information is essentially encoded by where the light falls in this region. So we don't need the actual color RGB pixels. Color, as I mentioned yesterday, is much more effective in teaching and outreach. So, but what's amazing is, let's just look at that dip. It's pretty pronounced. And look, if I pull this capture line away, notice that dip is still there. That, and I guess, again, to be more professional, I ought to be using absorption feature. Dip is more intuitive to people in the beginning. But isn't that pretty amazing? And you'll find a lot of things like that. Even rotation does not affect things that greatly. Even though, again, this isn't a spectroscopic feature, it's an artifact of the camera. Let me pull up the rotate and just do some rotating. Watch that feature there and watch how it continues to be there. It's still there. In fact, it got a little better for a moment. And that feature is still there. So exact rotation isn't critical, but it's certainly something you want to aim for. This 2 decimal places, adding a decimal place here, this was something that our beloved Richard Berry asked for when he started using the software. And again, it's Richard Berry, of course I'm going to add that feature. I don't know how many people are using it unless they're, again, into very precise work and advanced work. So let's talk about exposure levels here. I'm going to pop up our histogram. Oh, it's over here on my other screen. Let's see, is there another question? Yeah, no other questions yet. So this is, again, just, and you're probably familiar with this kind of data. This is just a map of the pixel values. We really just want to focus on this region here. So instead of having this very wide display, I'm going to do a cropping feature. It's really just a, I don't know what to call it. It's not cropping, but this is our region of interest with the control key and my left mouse button. And now we can see very clearly that data, and you can even see it's sort of spherical like the star, but nothing looks overexposed. Those are all under the 255 that's for this 8-bit image. Rspec will handle 32-bit FITS images with no problems. It's generally not necessary for the kind of work we do, but you can configure it for 32 bits again on the options screen here. So the 3D pixel map is a much more effective way to look at the data. So this, again, if we look at these axes, this is the column in the image. So that's the column along here. This is the image row, which is this vertical area. And of course, this is the brightness of that region. So, and we can rotate this around and we can look at this and go, well, you know, And in fact, just to help you with your understanding, this shape is that shape when we're viewing it edge on like this. But typically it's more interesting to look at it this way and you get better data. If you look at this, you might think, well, nothing is really, we're not flat topped here. It doesn't look like we've saturated any pixels. We're right up to 255 or, you know, 64K if we're running with a FITS image. But of course, this is a color image and we've got 3 channels. So let's look at each channel and see what they look like. Whoa, look at that. Look how overexposed or how flat top. Those pixels are all saturated. Same thing with the green and the red. So even though we're going to get some spectra information out of this, and even though when we're looking at a standard pixel map of the composite RGB information, it looks like it's not overexposed, especially over here in this region here. But then when we look at the blue, it's massively overexposed. I'm always surprised that we can even get information out of this. So exposure levels are important. And again, a rule of thumb for those of you who haven't done this before, and that is when you put a grading in your light path, let's think about grading this first. And that is, if you're just imaging a star, you know, the pixels from the star are all falling within the photons from the star are all falling on a handful of pixels. So, you know, a dozen, or I don't know really how many. It would, of course, depend on a lot of parameters on your setup, pixel size and so forth. But when you pick off with a grading and spread some of those out over here, you've now taken that same total number of photons. The star's not providing any new photons when you put a grading in the light path, and it's spreading them out across hundreds of pixels. And in fact, that was something I had intended to show you earlier. Let's come over here. I'm not going to pop up the full show in PowerPoint. We can just look at this graphic here. And this is in that Getting Started manual under the Help menu. It's from that manual. You want the grading to be approximately in a position where the spectrum is between, say, 200 and 400 pixels. If it's too far away, the spectrum is spread out too much, and you don't get any additional resolution, but you lose, basically, the signal-noise ratio just deteriorates. So, and this is all written up in the user guide, the Getting Started guide. So where is that thing? I have too many screens here. So we want to adjust our exposure levels on our camera so that if it's in color, all 3 channels, or if it's more typically mono, that we don't have anything overexposed. So that's one of the things, much like any of the other imaging that you've done, if you've done any. So I'm going to switch here to a different image that is in much better shape, and that is another Vega image. And we'll pop up the rotate command and we'll rotate it around, try and figure out how to rotate it. And there's just the issue, Patrick, you had mentioned. I went the wrong direction. There we go. And it's a little bit unaligned. There we go. So notice that this flashes red when there's rotation in effect, because especially on video, rotation can be very expensive computationally. So that's my encouragement to have you over time eliminate the need for rotation. So now we can see some stronger features. Again, let's just bracket in the whole image this time and take a look at, no, in fact, still, I'm going to hold the control key down and just look at that region. And that looks better. Let's look at even this one is saturated. Look at that. Isn't that amazing? But even with the saturation, we're going to get some usable data. These features aren't going to be nearly as deep as if we had data that was less overexposed. But let's continue with this one. So that's the exposure issue. Now, what's the other thing, of course, in our imaging is focusing. And focusing is a little tricky with spectra because it's not focusing on the star. It would be great if it was, but let me show you why it's not. There. So this is also in that Getting Started manual. So there's our star, and there's a star analyzer grading, and the starlight comes straight through. This is the diffracted light, and look, it has to, travel different distances each of these colors is traveling a different distance, and all three are traveling a different distance than the zero-order star. You can see there's the radius of this distance here. So starting out, definitely focus on the star. And then, and this is where the beauty of real-time comes in, or pseudo real-time if you're using this box. That is, if you've bracketed things in, take a look at the spectrum and see how deep your features are. This is another reason we want to start on a type A star. Because a type A star is going to have very clear features. And if you aren't seeing any, then there's something wrong, focus or exposure, or you've got the wrong target or something like that. So tweaking your exposure is really important, of course, because we want to maximize the amount of light in the given region. And the Getting Started manual talks about how to use a mask to do that. It's not that hard, and the good news is once you've figured out what the offset is from your typical focus on a star, maybe it's a quarter turn of your focusing knob, or 3 clicks if it's digital, then you can use that there going forward forever, and that makes life a lot easier. So, but initially, just focus the best you can on the star, then maybe try and tighten this up a little bit. Although when this is sharpest, it might not be the deepest absorption features. So I'm talking about it. It's taken longer to describe the things I've just described than it takes to do them. First, we did rotate. Now we did exposure levels. And of course, exposure and focus work hand in hand. Maybe you iterate a couple times through that to get the best exposure and focus you can, at which point these features will be the deepest. Now, how does focus affect images? Again, you might not be surprised by this. In the red is a really focused image, and this is also from that manual. And you can see here in the blue, it's less focused, even to the point if your focus isn't very good, or you're looking at a star without really deep features, you may not be able to see any features at all. Like down here, would we even spot that feature there if we didn't know to look for it? So that's the focusing trick and the exposure trick. The other thing I wanted to point out was, in fact, I want to go back to this just for a second. I'm not going to bother rotating it. See that flare at either end, especially there? That could be overexposure in the different sensitivities of my camera, but it also could be due to chromatic aberration in your setup. It turns out that spectroscopy is sensitive to chromatic aberration. And even though this is a hardware issue, I wanted to mention it here. And that is, you need, if you're using a refractor, to be an APO, or use an SCT, or something that doesn't have this kind of chromatic aberration. The first telescope, or the second time I went out, I tried using my Pronto. I wanted to see how big a telescope I needed. It's an older telescope, of course, beautifully made by Teleview, but it's actually called a fishtail because it flares out even more than this. And your spectrum has this really, the whole thing looks like a fish. It's just all this rounding. So again, I just wanted to point that out for you so that you don't have that problem yourselves. Okay, so along the lines of examining your spectrum, typically there's not much need to do this, but we do have a zoom screen here, which can be helpful, again, maybe more in teaching than not, but again, with your left mouse button and your mouse roller wheel, you can zoom in and out. You can also examine how close your orange lines are, and you can use these to move them closer. With really low signal, snugging these up as close as you can get is something that you'd want to do. So that's our magnifier. There is a feature that I'm not going to get into today that you can experiment with and watch tutorial videos on, and that's the subtract background feature. Again, one of the weaknesses of a slitless system is, if you think about it, this spectrum has been superimposed on the sky background. And so that noise is coming through. And if there's light pollution, especially if there's a gradient of any sort, the information in the background is going to really mess up your signal to noise. And you'd see it because this line would be much higher, right? This black area here isn't really black. It's got, 200 ADU units. And so it's a little redundant to say ADU units, isn't it? That's like analog digital units. like people who say ATM machines, same thing. So the background removal allows you to specify a region. In this case, 10 rows up, 10 rows. You can specify the region you want to remove the background in. When you do that, I guess I will show it to you since we're already here. Notice that this background noise subtracts down to 0. The spectrum typically does not get that much brighter, but one of the weaknesses you'll find, and this could be 6 months or a year and a half or however long, because frankly, not as many people move on to slit spectroscopy as one might think. But one of the limitations you'll find is longer and longer exposures with this, of course, you're getting more and more background noise. And so at some point, you just can't avoid that noise. So if you become a supernova hunter and you're going to do some classifying of supernovae, which I spoke about yesterday, you may find that that background noise eventually is what limits you in terms of what you're able to capture and actually extract useful information with features in the spectrum from. So let's see. So we've done focus. So now the final step in our initial steps here is to talk about this profile graph. Now notice how much time we spent just on the image. Again, there's nothing new there. It's just learning how to use a few tools that you've probably used in other imaging. Now I'm not going to click on live camera this time, but yeah, I actually had a really cool little demo I wanted to show you. Let's see if I can do that for you. I'm going to get out of full screen. I don't want you to see how I'm doing this, so I'm going to hide the left-hand side of the screen because it's a total kludge. But let's see if I can make it happen. I may or may not to be able to. There it is. So there's a really nice spectrum, isn't it? And I want to show you how focus can affect these in a more live manner. Especially if you're doing video spectroscopy, you'll actually see it behave like this in real time. And that is, as your focus changes, see how those features are changing? And you'll be able to see that in real time. That's another reason that and you can see I'm just changing, I'm simulating changing the focus here, and you can just see those features. And even if you're working manually, you're looking for the deepest feature. Now, again, I can't bear to keep you in suspense as to how I did that, at the risk of showing you something of very little utility. This is a Meteor Spectrum, and what I'm doing is the rotate screen has this slant box here that allows you to correct for the fact that the meteor is going at an angle through your field of view. You can see what's happening here. What it does is it simulates feature depth changing, so that and I didn't want to confuse you by showing you this because that's not the topic of our discussion today. So my apologies if that just took you down a path that you didn't want to go down. So this is our image. I don't know why it became mono, maybe a different image than I had, but again, you can see the same general information. So let's move on to the next step here, which is, as I mentioned, calibrating. And actually, I do want to find the right image. So let me do an open here and go to my desktop. I don't know why it's mono, but that's okay. We'll go over here to the video file. That'll work. Oh, it's all mono. Interesting. Let's see if we've got somehow a mono checkbox. Nope. I don't know why I went all mono. So there's a real bug. You've seen 2 bugs today. My God. But let's just pause this anyway. We'll pause it right there. Let's actually single step through and find a, there, that's actually, that looked like a great feature. I'm just looking for deep features. There, that's good. So calibration, just to talk a little bit about what we're seeing here. So what the software is doing is summing up each column. It's working its way across the image. Notice this is 1300 pixels across, so that's the width of my sensor. And it's just putting that total intensity by column here. And the software auto adjusts the auto scales the y-axis, does a lot of things for you automatically so that you can just do what you want to do without having to worry about zooming and panning and getting your views right. So Calibrating is the process of telling the software how fast the spectrum is spreading out. And that depends on how far your grating is from the sensor. So the way we do that, let's see, there's Patrick again. Patrick says, for some of us that have an electronic focuser, such as a Pegasus focus cube, could we use it to go to, first to go to a perfect focus of the star and then use the same defocus steps night after night to get a perfect focus of the spectrum? Yes, absolutely. That's the way to do it. And I was going to say the word, but true confession here, I don't know how to pronounce it right. The Bashnikov, or is he the dancer, masks that we use. And in the Getting Started manual, we describe using one of those to get perfect focus on the star and then just detune for the best profile over here. And then you can use that detune in the future off of a perfect star focus. So good question. Thanks for asking it. It took me 7 minutes to get back to you. My apologies. So calibrating is the process of telling the software, we don't want this x-axis in pixels because that's going to be different for every camera, right? And for every orientation or every position we put the star in. So it's really easy. And if I click on calibrate here, we can see very quickly, and there are videos, of course, on everything I've shown you, but not an introductory video that goes through it in the way that I am now. And now, having done it with you all, I'm going to produce that video this week at 2 minutes of 2 hours of production time per minute of finished video. We have to tell the software where the star is, and that's why we really emphasize getting the star in your image. There are ways to do this, but they're much less powerful and frustrating if you don't have the star. And you can see the bubble help right next to my mouse there, right there, is showing the x-axis value. Now, there are ways to do this with a lot more accuracy. We can do a barycenter fit, which is like a centroid on this two-dimensional object. Again, just to show you, when I click this, you can see an area down here popping up. There's videos on this. For most, again, of what we do, especially as newcomers, is just click on it and transfer that number across. It's pretty easy. If you don't want to click on it, or if as it turns out, if you're not in the right field and you click, the software is going to say, wait, that's not right. You need to be in the pixel field to tell it what pixel you're looking at. And notice I just guessed at where the peak is. Like I said, there are ways to do better when you decide you need that accuracy, which I suspect won't be for a long time, because there's so much to do that's interesting without actually getting that quantitative. So that is the zero order. That's the light that went straight through the grating. And we put a 0 here, and we've added that checkbox to make it a little easier. So that really, that's a free point. Of 2 points, 50% of them are just free. It's the star. So the second point is going to be, and this is, that cartoon, I actually should have it here, that cartoon of these physicists that have like several blackboards writing, and then at the bottom they write of expressions and formulas, and then they write and here a miracle occurs, and then they have their solution. This is one of those steps. This is a step, this is our bootstrap. We just have to know this answer. The giants have told us, and again on type A stars, the deepest feature just to the left of this peak is going to be, in most cases, our hydrogen beta line. So let's use my mouse roller wheel and roll in and try and get the approximate center of that Gaussian feature, Gaussian shaped. And that's our hydrogen beta line, which we could look up, but we could also just click that. So now we've entered 2 points. Let me double click to zoom out. And by the way, navigating on this screen is described under this help button, how to move around. The double click is the most useful of functions. And I want to show you, well, I'll show you one thing first. I'm going to click apply. This axis is now in angstroms. Now we can do scientific discussions. Now we can compare this to other spectra and other researchers and other days and so forth. So this is, for those of you who are mathematically inclined, this is just, it's a straight linear function, y equals mx plus b, where this is b, and m, the slope, is basically that number. How quick is the spectrum dispersing? Pretty amazing, huh? It's pretty straightforward. So having done that, some of the other things that we can do with this spectrum include, first of all, you saw me do this yesterday if you attended that presentation, pop up the element library. If we look here at Hydrogen Bomber, you can see the balloon help by my mouse there simply says, these are the common Hydrogen Bomber lines. If you care to see what the wavelengths are, there they are. And let's tell the software to display those features. And look how close we got. There's a feature there, 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 there. So, like I said, this is sufficient. Now we can really see that the impact of that Bayer filter here. That's a water line. Looking up here on the wall, that's that's oxygen at about 7,600. Let's see how close we get. You can see we're right on the money there. So we've now calibrated our spectrum. So there's a couple things that we can do here. First of all, we can save it, which is always nice using this, and let's see, it's 10:30, so I'm going to finish up in just a minute, using this floppy icon. We can also save it as a 1D, one-dimensional FITS file to save it to the AAVSO database. And when you do this, it will walk you through some questions. It wants to know who you are. You need to be registered at the AAVSO as an observer, and it wants to know a little bit more information about your image. So you can export this data, no problem at all. And also, if you just use the standard export, you get to export to, it's a text file that you can read back in here later. So the 1D FITS file you can read in also. The text file is a little bit easier. Suppose you're like, you want to do some Python programming with this extracted data. It's available to you in that text file. So that's the process of calibrating and acquiring an image. You can see it's pretty simple. I was worried actually as I was thinking about this presentation. Unlike Steve Shore, I didn't think about this while I was eating breakfast this morning. I've given it some thought in the past week or two as well as in the past 10 years. I wanted to show you just some of the pretty things we can do. We can synthesize the spectrum down here. What's interesting about that is the color is nice, but if you click on this little gear and go mono, you actually can see the features more clearly, which is something we've all heard about, maybe even experienced, and maybe that's a better presentation for you. It is a little hard given the dynamic range of the data. Again, if we overexpose this, these become clear. But again, the color also, let's just reset it. And the other thing we can do is click this fill box and get that. It's eye candy, but it's really good candy. This is really effective. So there's that robin egg blue hydrogen beta feature. Now, just one other thing to tell you, it's more cosmetic, and that is you may often see people labeling their graphs. So if we wanted to label that hydrogen beta, we can just come here and type in hydrogen beta, and it wants to know, well, let's put the word beta in there. And in fact, we can even right click and put the beta symbol there. And now we just click on the graph to tell it where we want that identifier to be, and then we can move it around. So there's lots of cosmetics which people like. It's interesting that how important all of us feel it is, because we again take on a certain ownership of our data here, and we like showing our data in a good way. So there's all sorts of things you can do in this labeling region. You might notice that the number of labels goes up to 144 or 143, and that's because of some solar observers, particularly one in Greece, who actually uses all those, believe it or not. So I think that's all we have time for today. The only other thing I wanted to show you was, I think we'll leave that for another time. But let me just emphasize that once you have this number, which is the dispersion that comes out when you enter these 2 points, you then never have to identify any features over here. As long as your grading stays the same distance from the sensor, in the future, excuse me, in the future to calibrate, you just identify the zero order and you're done using this 1 point calibration. All right, so that's it. Let's open it up for questions. If I can figure out how to. I'm going to stop sharing my screen to give me more controls. Paul asks, Go ahead.
Yes. Okay. No, I just want to say that Paul asked a question on the chat, not Q&A.
Oh, okay. Let's see. Paul Norris said, what are the advantages, disadvantages of JPEG versus RAW file? Well, as Olivier will confirm, when you get into really scientific data, you want every bit of precision you can get. For the kinds of things I'm showing you, for creating "Oh Be a Fine Girl, Kiss Me," the reason I stumbled on that, and I don't think I mentioned it yesterday, is I don't really like that acronym for "Oh Be a Fine Girl, Kiss Me," and there's one here I found on the web as I was looking around the other day for a substitute. It's okay, boomer, a fully green kilowatt matters. Obia FGKM. It's not particularly catchy. But so I think what you'll find, especially given how easy processing is here, is that whether it's a RAW or a JPEG or going back and forth from even 8-bit fits to 32-bit fits, it's not going to make a lot of difference in the kinds of imaging that I'm talking about with the samples. When you begin to want to create more scientific data, then, as I said, you want all the precision you can get so that you, again, especially if you're doing stacking. By the way, as I mentioned, I didn't want to reinvent the wheel, so stacking, if you were doing it, you'd be doing that outside the software. In video, we can stack in real time, but in FITS images, you do it on your own. And Lauren gave a great presentation showing the value of that yesterday. So let's see, other questions. Is there a way to incorporate a calibration light source? Yes, I didn't get to that, but typically what you would do would be, and I don't, let's just turn off all these labels, is you'd load the light source here. You can have two curves visible simultaneously. So not that it's going to be particularly interesting here, but let's see, there we go. So there's two curves. And then you're able to use the calibration, your lamp curve here on your data that would be visible over here. The other thing that I wanted to show you and didn't get a chance to, just really quickly in terms of calibration, is that built into the software is a reference series. It's called the Pickle Reference Library. It's a professional library, and it allows you to compare your data to a professional library. So for example, here we can see professional library in blue overlaid over our red spectrum, and we can see that we've got...
Tom, you have to share your screen. We don't see it.
Thank you very much. I really appreciate it. That's the second time I've made that mistake in 24 hours. Let's share the screen here. I'll do that quickly here. There we go. So what I did here was under reference, I opened up the reference library and selected a star that's the same star type as Vega. And you can see that curve here. And notice the corresponding features that match up, confirming that we've done things at least sanely, if not exactly. Now, the other thing to mention, which we won't get into today, is you'll notice that the professional data, this Planck-like curve, follows Wien's law and continues climbing from here, whereas our data drops. And that's, of course, because our camera sensor gets much less sensitive as we get into the blue region. And so there are ways to use this curve and a known star to come up with the QE curve of your entire system, not just your sensor, but also the grading, any introduced nonlinearity or nonlinear sensitivity in your telescope, as well as the air mass. And there's videos on how to do all of that so that your curve can be corrected so that it allows you to approximately tell the star temperature. Professionals use features in the spectrum, not the shape of the curve. And there's a discussion on that under this menu here. Other questions that people may have? Where was the convert to mono option? Oh, OB a fine grade kills me. Oh boy, F grade kills me. I like that, Tony. The mono option is on the options screen. Let me just share my screen again. And maybe I should just continue sharing my screen. Let's come up here and here under force grayscale. There's really no difference in the results that you're going to get in those. At one time, I thought that the software would be faster rather than having to add up all those RGB values to a composite final grayscale value. But as it turns out, it's no faster. Other questions people may have. I can't see the question screen when I'm sharing my screen, so let's come out. How do we zoom if we're using a trackpad? Great question. I think it's the page up and page down button. That, again, maybe I should just leave my screen shared the whole time. Share screen. There we go. Let's see if it says it here. It doesn't. It says it in one of the videos, but it is page up, page down. So that'll do it for you. Other questions there under Q&A? I don't see any. And are there any under chat, Olivier?
Nothing.
Okay.
Yes, a question from Patrick just now. Oh, no, just thank you.
I see that.
Okay.
Well, thank you. Thank you, Patrick. I appreciate it. And Jim, thanks for the heads up that I wasn't sharing my screen earlier. Thanks, Olivier, for being here and catching me on that. You know, sometimes, especially when I have very qualified pro-am people observing me like Olivier, I'm a little paranoid because a lot of people consider Rspec a toy. And I think what is important to recognize is that we all have to walk before we run. I don't want to minimize the amount of work and the importance of doing very, very repeatable scientific observations. Some of those steps are available in Rspec. And again, as you get into more sophisticated imaging and more sophisticated equipment, that becomes more and more important. But I think the important thing for most of us, especially as we're trying to bring people into the field and get people started, is that we give them a pathway to do that. So listen, everybody, I appreciate all of you attending today. You all hopefully know rspec-astro is my website. I'm always happy to hear from you. I'm going to put my email address here. My name is Tom Field, so Field Tested Systems is maybe a little too cute. And the website you all know. Let me know how I can help. I love helping people. We're more or less on time, and let's get back to the assembled group. Is there anything else anybody has to say? Yes, Rspec does work, Rick, on high-res images. Depends on how high-res you mean. If you're talking about spectroscopically, yeah, we have lots of people using Rspec with ALPEs and other higher resolution devices. There's a couple more steps. Instead of just using 2 points to calibrate, you may want to use our nonlinear calibration where you can do a polynomial fit and look at your residuals, and all of that is included in the software. Anyway, thank you all again, Olivier. Thanks for hanging out today. I hope you had a good stiff cup of coffee there to keep you awake, and I appreciate everybody's attendance. Have a great afternoon.
Okay, thank you very much, Tom, for this presentation. It's time, I think it's time now to come back to the main session. So see you soon on the main session. Bye-bye, everybody.
Bye, you're welcome, T Gong.